Hi, everybody. This is Stockton Maxwell with the Department of Geospatial Science, Radford University. And today I'm going to be doing a short tutorial on how to read in raw tree ring data sets into R and create a chronology. So let's start out with a screen share. Okay, so here we have the R console open up in RStudio. And for those of you that are not familiar with this, I'll just give you a brief setup. In the top left here, we have the R code that we have in an R script or a text file, essentially, with a .r extension onto it. And for this, we can run most of this code as I have set up, and I'll upload this R file to my website if you would like to follow along with the sample data set that I'm using in my tree ring analysis seminar this semester. To start out, we need to set our working directory. And so we can either use a setwd function and put in our pathway. This will allow you to read files and write files to a specific directory on your computer. If we want to do it through the sessions menu, we can navigate to set working directory and choose directory. And you can choose kind of any folder that you want. So I have an analysis folder for my course. Now that we have the location where we're going to be working out of set, you will need to install libraries for this analysis. These are the packages that will be used in the R code. And a package is essentially a bunch of functions that have already been written by other scholars and scientists to aid you in your work to create this more open science, allowing for more people to participate. These packages often build off of each other. And so you will see functions in dplR that would be used in TreeClimb, for example. I have all these packages already installed, but I will need to load those libraries. And so I'll highlight and run these lines of code so that the functions will be available to be used. You need to call up the libraries first. So now that the libraries have been read in, we can begin some analysis. So the first section, we're going to be using code from the dplR package, or the Dendro Chronology Program library in R. This was started by Andy Bunn and improved upon and added to by other scholars with Andy's help. In here, you can do things like run cophacia, or using programs in statistical analysis similar to cophacia for cross-dating. And so I'll show you a couple of those things first, because to create a chronology, it's got to be well dated. But cross-dating is kind of a separate venture from this. I'm just going to show you the highlights. So if we want to read in our data set, this would assume that we have an RWL file. An RWL file is a text file that looks like this. This text file is in the Tucson tree ring width format, and it has a unique type of format to it. So here we have the decades, and here we have the measurement in each year. That measurement is 3.932 millimeters, and it is that number of characters because the precision of the measurement coming out of Coup Recorder is to 3 decimal places. And so this would be the year 1920, and this would be the year 1921, the measurement for that. So each row is a decade, and then it ends with the code -9999. And that is a code that was often used to say, stop reading the file. So this is the format that you need to have it in, and you would need to export something like this or save it in Coup Recorder or a similar tree ring analysis program. To read that file in, we can run this function called read.tucson, and it has just one main argument in here, although we could specify other arguments, but we need to read in SALU_final. This is a collection of white oak tree ring measurements from SALU Conservancy, collected as part of my tree ring seminar this semester. And I am going to assign it this name, grow.rwl, and it's going to add that over into our environment section once we run the entire line. Now that that's happened, you can see that it's read in each of the 38 series, and it has a begin year and end year for each of it. If we open up grow.rwl, essentially what it did was it read it in and it transformed that data into rows and columns. And so each column is a tree or a tree core, each row is a year, and in each cell there is a measurement. So it's simply just reading in the file and transforming it to a different format. Now we want to run some statistical analysis to see how well we've done with dating. And again, I've already worked on this chronology outside of R using the Xdata app, which essentially runs R in the background. I highly recommend that you use the Xdata app or the built-in functions, the dplR for cross-dating. It tends to be a little bit more intuitive because of the visual feedback that you get from running the functions or using the Shiny app that Andy Bunn has created. Otherwise, you are welcome to run this in Cophatia. I often find, though, for new dendros that reading text line after text line in Cophatia is not as intuitive as some of these other types of functions we can use in dplR or in the Xdata app. But we can run some stats. So RWL stats, we can run and call up our new data set there, our new data frame called grow.rwl. If I run that, we can see we have now a series of statistics, and it will give us the last year for the measurement file, the number of years, the mean growth, median growth, the standard deviation of growth, the skewness of those measurements, the Gini coefficient, which is a measure of equality of values. And so 1 being all measurements are the same and 0 meaning none of them are the same. You wouldn't want everything to be the same because then it wouldn't be responding to climate or ecological things. And you wouldn't want everyone to be different. And then finally, we have AR. This is the auto regression coefficient here, how much autocorrelation there is, or persistence in growth from year to year. How much is last year affecting this year? Then we can write that to a CSV file, a text file if we'd like. And so I'll just do that and save it into my working directory. We could also create a segment length plot. This is a good way to view your data and see the sample depth that you have and so forth. And you can see that some of the cores that we lost wood on the outside, probably out in the field or on the belt sander. If we want to save that, we can go to the export button and hit save image as. And you can adjust the file type. I'll just use JPEG and we'll call this seg_plot. And this will save it to my file. If we want to change the size of it, we can do it like that real quick. Go ahead and hit save. Another statistic we might want to do is mean sensitivity. So I'll run this line and it will just print out a value over here. And that value of 0.2275, so forth, that is a measure of how much variability and growth there is from year to year. Again, with 1 being that every tree ring is different and 0 meaning no tree rings are different from year to year. This is an overall broad metric that you can use to help describe your tree ring chronology. Typically, yeah, you probably want something with some variability, so like a 0.2 or higher, but if it's a 0.8, maybe that's too much variability, but it really depends on your site and the interpretation of that value. Now we can do an RWL report using our rwl.report function. And if we run that and then print it, you can see that this pulls up a series of different types of figures that give you the number of series, number of measurements, average length of the series, and so forth. And most importantly, probably your inter-series correlation of 0.59. So this is a relatively young stand of trees. We have a couple old ones in there, and they date pretty well, but there is some what we call ecological noise if you're a dendroclimatologist. And we may want better dating, but this is a closed canopy ecosystem with a fair amount of disturbance to it. And so a value of above 0.5 for this stand is actually pretty good. Now, we could run some cross-dating functions, and again, highly recommend the Shiny app from Andy Bunn and for Xdata, and there's the the web address for it, but I can run a couple lines of code to show you what that's doing in the background. Here we have run the correlation analysis, and it's best explained by just opening up this figure. What this function has done is it's taken individual tree cores and it's calculated 50-year segments from one tree core to the average growth or the calculated chronology from all the other trees in that data set. So it'll take out one tree core, calculate a chronology or the average tree growth at that site, and then it will compare your tree to the rest of them. And then it can do that by 50-year segments. So when you look at this, if you have misdated segments, you would have a low correlation for that 50-year segment with the overall reference chronology calculated for the site. This site has already been dated, so we don't have any flagged segments, but you can have a flagged segment for a few different reasons, but typically it's going to be because you have a low correlation that is driven by some misdating. And with a 50-year segment, you would need a correlation of 0.32 at a 0.05 p-value to be significant. And so this one dates really well. So if we wanted to keep that, we could go and export that image as well. Now we might be interested in an individual series, and so we could pull up that individual series with this argument. And this will allow us to examine individual cores that may be challenging. So if we zoom in on this one, we can see the red is the individual series that we've measured, the master or the reference chronology calculated from the remaining cores at that site. You can see that plotted and kind of see where they go off. Here you can see the correlations with those 50-year overlapping segments. This tree core is pretty well dated, and here you can see the line of best fit from the individual series measurements to the master chronology. Again, you can save all of these figures as well. Now, we might want to calculate and get all of those interseries correlation measurements and name it an object inter, and then write that to a CSV. This will allow us to save that for later, and it will save all of these pairs of correlation values. And so if we wanted to look at that inter CSV correlations, we can see how well each tree is correlated with the reference or master chronology. Now, this chronology has been dated, but typically if you were using dplR, you would iterate through this code, picking out problem cores, examining them. But again, the Xator app provides a lot of visuals that are driven by the dplR code. Another plot that I often make just to have a quick look at the data is the spaghetti plot. And the spaghetti plot is a nice one because you can see stand dynamics things pop out. And so in this section right here, I'm seeing a few trees that had a big growth release. I'm seeing some disturbances here, maybe late 1950s that seem to be common across the stand. And here you can start to get at endogenous versus exogenous disturbances and determine if something inside the stand is happening idiosyncratically to a few trees, or an exogenous disturbance like a windstorm or ice storm event has affected all of the trees. Now, for dendroclimatology, you're going to need a single tree time series for analysis with climate data, often monthly climate data. And I have a previous video on where to source some of that climate data and a quick bit about formatting. But for now, we actually need that time series. And so what we want to do is we want to detrend and standardize our tree ring data set so that they are all on the same scale. And we remove growth trends that may be related to the age of the tree, how long it's been living, and to the ecological disturbance that may be happening in that stand. Because with a chronology for dendroclimatology and climate response analysis, we are trying to hone in on what is the common climate signal at the site. You can do this type of analysis in the program RSTAN that is Ed Cook's main piece of software that you may interact with. RSTAN is an amazingly powerful piece of software, and perhaps in the future we can dig down into that deeper, but fundamentally we need to take raw ring width data, fit a curve to it, and take either the residual values or the difference values, or a ratio of actual to predicted. So it's best to look at this with an example because we need to get all of our data on the same scale because some trees grow bigger, some trees grow smaller, and if we were to average them together, that would be just for the raw data. But we need to get rid of some of those growth trends as well. So there's an interactive detrending function called i.detrend. It will pull in that grow.rwl data frame. And there are some other arguments that you can specify in there, but you can just go with the defaults and get pretty good at understanding what is happening to your data set. So let's go ahead and start this out and run it. Here, it pulled up the first tree ring data set, Sela 02. We have growth in millimeters up here, so this is the raw data, and here we can see the line showing change in growth from year to year. And then we have a series of options that fit a curve to that data set to help remove trends that may be related to the age of the tree or changes in growth because of ecology. So we have a spline, a cubic smoothing spline, a negative exponential curve that will decline towards an asymptote, a horizontal line just through the mean of the tree growth. We could just have the raw data set down here. The Friedman Super Smoother is a very adaptive smoothing spline that can adapt locally. And so it's really good when you have big increases in growth or suppressions. And then there's also the Hugershoff function that is kind of adaptive right in the beginning of the tree ring series. And then we'll go into a negative exponential, or you have the option of fitting the standard line through it, just a straight linear regression. And so each one of these will take the value that is predicted by the curve and create a ratio of actual to predicted. Then it will transfer that value and scale it to a mean of 1 and bring it down here and create the ring width index with the average of 1 through it. The idea here is that you need to understand what these detrending techniques are doing to your data set. What types of signals are you keeping and what are you removing? For me as a dendroclimatologist, I'm looking to remove a lot of those signals that are associated with ecological changes, like a tree falling down next to the tree that I cored, causing a growth release. That's clearly not climate, and so we would like to remove that so we have a chronology that's calculated that we think is retaining as much climate information as possible. And so you can see from different trees in here how it will behave. And so here, often a good option is just using a cubic smoothing spline if you're just starting out. So I'll start out and just do 1, hit enter, and now it's saved that, and it's brought up my next tree ring series, 101A. This one's growing a little bit differently. It's got a big growth increase here. And we can see that if we were to fit this brown spline to it, we would still keep some of these artifacts in of the growth, release, and suppressions there. If we use the Friedman Super Smoother, it is going to be very flexible and get up and down through those growth, releases, and suppressions and do really well here at the end. Often when tree ring scientists are looking at their tree cores to see how well their splines and different curves are fitting, they're looking at a couple specific areas. The beginning of the tree ring series near the pith, so the oldest part of the tree, and then the youngest part of the most recent growth of the tree. So are we overfitting or underfitting at those ends? End fitting is a big challenge when you have straight line techniques that may overshoot or undershoot. For example, if we were to put the horizontal line just through the mean of this, that would cause this tree to seemingly grow at a very low rate for much of its life because of this growth release up here increasing the mean growth. The negative exponential, on the other hand, just right here at the bottom, this undershoots and causes a growth increase. And so we have to be careful about what signals we're retaining, particularly at the beginning and end of the tree ring series. Now, I won't go through every single tree here, but what I will say is that you're typically going to want to use 1 or 2 standardization and detrending techniques to create a tree ring chronology. You don't want to pick the flavor for every single tree core because it's not replicable. Unless, well, I guess you could include the technique for every single tree and publish that metadata. However, you typically want to use one or two techniques. So maybe you do a negative exponential. If that fails, maybe you fit a cubic smoothing spline. In the Eastern United States, I'm often using cubic smoothing splines or the Friedman super smoother because I often have stand dynamics that I need to control for. And so I'm just going to add in and use the cubic smoothing spline for everything here, just shooting through all the trees at the site. And you can see them going by in the graphs area. And so now that I have done that, and we have fit all of those curves, we could go and plot that now. Typically what I do is I use the i.detrend, the interactive detrending, to help me understand what is going on at the site, how the trees are growing, how the curves fit the ends before I plot anything. Then I can do a spaghetti plot. Now this is not with the raw ringlet data, this is with the standardized data. And you can see that it's gotten rid of a lot of the age-related growth trends where trees often grow a lot when they're young and decline steadily over time. But we can still see some of the stand dynamics that have remained in here that are likely not due to changes in climate. So it's not always perfect. But on average, we're trying to retain as much climate and get rid of as much ecology as possible. To detrend all at once, I would run this line and just pull in grow.rwl and choose the spline method. This will allow me to get everything at once. Then I can look at some statistics of that and pull up that, and so we can see the number of cores. We can see the average sample size through time. And then probably most important, the R bar, which is the kind of the average correlations that we can get across segments, and the EPS, which is a measure of the expressed population signal. And the idea here is a hypothetically perfect tree ring chronology would be a 1.0, meaning all the trees are saying the same thing. And as you go towards 0, you're beginning to lose a common signal. So the expressed population signal, we often kind of default to a 0.85 threshold. If it falls below that, it's becoming a little bit too noisy, and we're not probably honing in on that climate signal as much. Now that's just the one snapshot. We can do this, and we can write that to file, and we can do this in a running manner using 50-year segments that overlap by 25 years, similar to what Cofecha and the dplR app did for dating. And that looks just a little bit different. And so when we look at the running statistics, we can see here, it breaks it up by those 50-year segments. And in particular, if I'm doing climate reconstruction, I want to see if all those 50-year segments have values above 0.85 for the EPS, or expressed population signal. If it declines, it's an indicator that that tree ring chronology may not be retaining a lot of climate signal. This is very common as you go back in time for the EPS to decline, because you have fewer tree ring cores in trees calculating the average growth during that time period, and you have it often an increase in variability as sample size declines. Now, we need to actually build the chronology. That first step there was interactive detrending that allowed us to fit a curve through it and then calculate the actual value to the predicted value and put that on a scale with an average of 1. That detrends it and gets rid of growth trends and other types of ecological disturbances. Now we would typically follow this up with autoregressive modeling if we want to create what's called the residual chronology that removes a bit of that persistence or the influence of the previous year's growth on this year's growth. We know that's kind of a biological function of using those stored sugars, and so the residual chronology will try to minimize that. Here, we're going to use the cron function. We're going to pull in grow.rwi that we just created up here when we detrended everything at once. You could put a prefix in there for your site, like a 3-character code. We are going to use what's called a by-weight robust mean. This will control for outlier values in a given year. And then we will use pre-whitening. Pre-whitening means that we are going to calculate autoregressive models for individual tree ring series, and then apply an AR model to remove some of that year-to-year persistence. And so we would have true typed in there. If I run that function and then plot it, we get a figure like this on the right. And this shows in the background, the gray shade is the sample depth here on the right side. This is the ring width index with an average of 1 through it. And then we can see the average growth after we have done our detrending and standardization with the autoregressive model. And so we can see that. And then this red line is to look at some of that low frequency variability, how things change over decades or so. We could save that image through this menu here. Then we might want to write that chronology to a file. We can call it chronology.csv if we want to call it up later or read it in later. Now you can also create a chronology with the standardized model that keeps in the autocorrelation or some of that persistence from year to year. This will keep in what we call more low frequency variability. The idea here is that you may have a climate variable that has autoregressive properties or autocorrelation between the value in 1 year and the next. If that's the case, maybe we want to keep that in the model. And so we can run this again and just change this to false. So we do not want to pre-whiten it. Pre-whitening is essentially getting rid of that persistence from year to year. So go ahead and run that. And we can create a plot. And you'll see the plot change down here on the bottom right. And so we can begin to compare the two different methods from the residual chronology to the standard chronology. And you can see how the standard chronology has more of that low frequency or almost decadal length variability retained in it because we did not remove the autocorrelation. So these are the key functions that you're going to need to use in R to develop your first chronology. Now, this is just a quick overview. You may need to dig into it. And so you're going to need to look at the help menu, and you can type in and look for specific arguments that you may want to change in the dplR app. And you can look at each one of those here. Each one of those arguments and functions has examples for the arguments that you can use to start out with, or you can use the code that I'll be providing up on the website. Okay, that is a lot of information. Try to get started with your own data. And essentially, if you do what I did, if you read in your RWL file right here, you can just put your cursor next to each line and hit the run button sequentially, and it will do a lot of this work for you, and you can save the graphs as they come up. Okay, everybody. Good luck with your analysis. I'll see you on the other side.